Okay, so yeah, today is lecture three, but what I'm going to do is I'm going to go over the assignment one, and we have homework. Ayash has submitted homework, and so this is mainly this course is mainly for those who haven't done measure theory, but kind of planning to do rigorous probability theory. So, and then these kids have done real analysis, and but uh, but they haven't done uh, mathematics necessarily for a couple of years, so they're rusty on writing proofs and everything. So I decided to take a day off, and then day like away from the lecturing, and then go through these things carefully. And yeah, it's actually the real target audience for this course are not the mathematics special students or like mathematics majors, but people who are into finance or like doing statistics and things like that. So it's I mean, that's the magic of this Rosenthal's book, and yeah. So yeah, we'll go through it. Yeah, so we'll go through these homework problems carefully. Okay, and starting next like Thursday I'll start new material again. Okay, so let's go through it. So the first problem is this one. Let me see. Uh, it's exercise 1.3.1. So we're given that omega is this, and we're given that probability of omega, probability of empty set is 0. So the p is a function, and we have this, whole set is 1, and then we have this. Okay, so from the problem we can see, I mean, in this case, the um, yeah, okay, so we'll get into the sigma algebras, but the uh, we need to prove that P is countably additive if and only if P of 2 is 3 over 4. Okay, now let's go back. So here is the solution. So the first line, suppose omega is this, okay, and then uh, so and let's it is better to put this line specifying the sigma algebra uh, before the probability. Okay, I know that the problem hasn't done it, so that's a setup. We have the omega, and then we are working with the sigma algebra, this thing. Okay, and now the p is a function. We want p to be a function from the sigma algebra f into the interval 0, 1, and and we're given that P is defined for three of the sets, three of the elements of the sigma algebra. Okay, and so and our what we need to prove is P is a countable additive measure. P is countably additive if and only if P of the fourth element of the sigma algebra is 1/4. Okay, so let me write that down a little bit. Okay. So, we given omega is this, and f given, and p is defined on the set, empty set, 1, 2, and 1. Okay. Let me call it p delta. Oh, look, I mean, this is, uh, it is a trivial point, but I mean, they call it a probability, like the function p, but it is defined only on these things. Okay. Now, uh, need to show. Let me write it this way. Let's say that we have a function p defined on here, and let omega is this, this is this, and f is a function from f into here with uh, p of empty set is 0, p of this set is 1/4, right? I think it was 1/4. Yeah. Show that p is a countable additive uh, probability, which countable additive probability. You can put this thing in the bracket because countable additivity is part of the definition of the probability. Show that this happens if and only if p of 3 or 4 is wait, p of the set 2. Okay, so this is the problem. Okay, now this is very trivial, but we have to be very, very, very careful. Okay, and we're gonna write like a very complicated arguments later on. Okay. So let me go back to the view solution. Okay. Again, like thank you very much for doing this thing. Okay. And okay. So we kind of basically rewrote the first three lines. Okay. Good. And kind of the yeah. So now it is uh, now it is framed as P is a function that's defined on the sigma algebra, and we know like three values of that function, and now now the problem is the value of the fourth point determines if it is a probability or not. Okay. Good. That's clear, right? Ayesh, Bhumika.
Yes, sir. Correct.
Okay. Okay. So now let's go to the now let's write the proof. Okay. Proof. So we are proving the now now our goal is to investigate this first direction. So you have shown that if you assume that P is a probability, then the P of 2 has to be 3 over 4. Okay. And this part is basically correct. It is correct, and then you're working with the second part. Okay. Good. Good.
Yes.
Okay. Okay. Now, uh, so let me go back and write down this part. Okay. Okay, so we're doing this direction. So we have this if and only if, and we have to prove two directions in proving this direction, forward direction. Okay. Okay, so in the forward direction, so we assume E. Give me a second. Okay. Okay, so we assume that P is a measure, P is a probability. No. So then so then we have P. We write this, leave a blank here. And we use the fact that P of 1 comma 2 has to be equal to P of 1 plus P of 2. Okay. And so this will give you P of 2 equals 304. You plug in numbers in. Okay. So that completes one direction. Okay. And now for the other direction, from the other direction, so let me go back. So let me go back to so for the other direction, we can assume P of 2 is 304. Okay. So we need to show that P is a probability. Okay, so that's what we need to do. Okay, so let me go back. To your solution. So so what you have, so this is the this is the kind of the so this part needs more detail. Okay, and so so what you have shown this P of 1 union 2 is this. Okay, and then you get this. Okay, and then we say that therefore P is countably additive. Okay, so that so you complete the other direction by this this computation. Okay, and then you write the statement. Okay, but this is trouble. Okay, so what you need to show that that this P that is defined on this. So the first thing to realize that once you have that number P of 2 equals 304, you have the complete definition of the function P, which is from f into these guys, and then you need to show that this probability P is countably additive. Okay, so the countable additivity that requires showing this property for a countable sequence of sets. Okay. Okay, and then we both understand that you take a countable sequence of disjoint sets, then most of the uh, elements of that sequence should be empty sets. Okay, so we kind of it reduces the verifying the countable additivity property reduces to verifying the finite additivity property. Okay, and we are kind of saying implicitly that what we're really using is if the sigma algebra has only finitely many sets, then verifying the countable additivity is same as verifying the finitely additivity. Okay, and then in this case you have like yeah, in this case you kind of by using that you can I mean you can verify finitely additivity with uh, like if you don't take like empty set like 1,000 times, it is still finite. We can like exclude that those type of scenarios, and then you can like reasonably say that you only need to verify this property for finitely many cases. Okay, and then you can say like okay uh, in that case it's only finitely many cases to verify, and then and you have verified one of those cases. For example, you need to verify, here is another example, we need to verify that P of set 1 union the empty set equals P of 1. That's part of the countable additivity. Okay, or like the finite additivity. So you have like a lot of other cases, and so when you write it like this, it looks like you're thinking that this is the only case. Okay, but it is important to notice that there are finitely many cases, and then and we both agree that it is finitely many cases. It is simple computation to verify all that finitely many cases, and we don't have to do it explicitly. Okay, but it is better to mention that than doing one computation, one case. Okay, so the goal is to um, kind of get to that, and then you can write this something like this, like for example, we have this case. Okay, good. So the key is to uh, reducing the countable additivity property to finitely many cases. Okay, good. So
Yes, sir. Got it.
you understood the point, right?
Yeah, yeah.
So and actually so that's you going back and forth from the countable additivity to finitely additivity. Okay, so now so let me go back to the proof. Uh, Again, it is a minor point, but it is if you write something like this, like if you just leave that one case, and then that shows that there's trouble. Okay, it is better to explain it in words and then maybe like do one computation that involves P of 2. Okay, so let's go back and let me go back here too. So I put a blank here. So what we're really using, if P is a probability, uh, then we have the countable additivity, right? So that means you cannot actually use this thing in theory. What we really should be doing, we have to pick a sequence of sets where the first set is A1, first set is A1 is 1 and A2 is 2, and then the A3 all the way up to the rest of the sets are empty sets. Okay, so what we are really going at is uh, verifying uh, uh, the countable activity. You can do it in finitely many steps. That's what we're after. Okay, so so the better thing to do in this case, you introduce a little lemma or fact. Okay. Okay, so let me write this thing. Lemma below. Uh, okay, so let me write the lemma. Uh, let omega uh, be a set and f be a subset of A, a finite sigma algebra. So we are not assuming that omega is a finite set, but we are assuming that sigma algebra is finite. Okay. Let P be a function defined in here. So in here, this is just a function, okay? Good. And how do you do this? It's I mean, the trouble is the empty sets. We don't want to create. Uh, let me add that as a as a property of P. Let F be such that uh, such that I mean, the first property is for the probability is that the probability is between 0 and 1. So that's already included in here. And let's look at the, let's include this property too, is that P of empty set is 0 and P of the whole set is 1. Okay. P is the probability measure. Now P is a probability if and only if for any A1, A2 up to AN, which are subsets of which are elements in here, such that for any pairwise disjoint. A1, A2, AN, and here. For any, let's put the non-empty here. For any non-empty, pairwise disjoint sets. In here we have we have this probability of the union k equals 1 up to n, ak is equal to this. Okay, so this takes away the let's take away the kind of the verifying things with the empty sets part. Okay. Good.
Yes, sir.
Yeah. Say it again.
Yes, sir, I'm fine.
Okay. Okay. Oh, you have
Alright.
background noise. Okay. Okay. This. Now here is the furthermore. There are only finitely many uh, finitely many collections. Even up to n. That there are only finitely many cases. Of AIs. So in other words, like if you think of this set A, which is these sequences AI, I is from 1 up to n, such that A1 up to AN are in here, and AI is not equal to the empty set, and AI is are pairwise disjoint. Okay, so these are the so this lemma tells you that these are the cases we need to verify. Okay, but I'm saying like the very extremely trivial thing that I'm like playing with, but it is good to kind of formulate this thing. Okay. So once you have that lemma, kind of this is telling you that it is enough to check this property for finitely many cases. Okay. So let me finish the proof here by the following lemma, by using the following lemma. It is easy to verify P is probability. Okay, and then you add here, for example, and then you go through the one case you had. Okay, good. So I mean, even if you don't introduce this lemma, it is better to write a sentence like this. Okay. You write something like, since our sigma algebra has only finitely many elements, we can verify that piece of probability by checking finitely many conditions. Okay. and then you say, like, for example, we write it like that. We don't have to introduce the lemma. Okay, but yeah. Okay, so let me call this thing the let me put this thing as the problem 12. Okay. Uh, Good. Any questions?
No, sir. It's there.
It's okay, right? The basically, so one direction is easy. If this is a probability, then you have this condition, because we can prove this condition by adding bunch of empty sets. Okay. And on the other hand, if we have this condition, if you want to prove that it is a probability, so you take a sequence of elements of the sigma algebra, and then you first show that uh, we should have finitely many non-empty sets, and everything else has to be empty. Okay. And then you reduce that condition for the countable additivity into something like this. Okay. And that because you'll have a bunch of zeros otherwise. Okay. So but we have this, so that means we have the in this way you can verify the countable additivity. Okay. And then the final step is this. uh, so how do you verify this? How do you want to show that this is yeah, I think you can go by showing that if you have A1, A2, I mean, first you can show that the number of these sets n, like n, that number n has to be less than or equal to the number of elements of the sigma algebra F, because we know that the F is finite. we can show that these sets are pairwise disjoint, and so for example A1 cannot be equal to A2 because okay, because they are non-empty. They have all these things are non-empty, so that means they cannot be pairwise disjoint and not equal to the empty set. Okay, so that means this number n is less than or equal to the size of f. Okay, and then now this curly a, this big curly a is not just it's this type of sequences of sets from f. But if you show that this simple n, the length of the sequence has to be less than the size of f, and it's just a permutation problem. For the first slot, we have f choices, and then the first, yeah. So all I'm saying, you can prove that can actually prove that size of this a is less than equal to the size of the sigma algebra raised to the size of the sigma algebra. Okay. You can prove that first you can show that n is less than or equal to the size of the sigma algebra. And then once you have that, then you can show that the capital A, that curly A is less than that. Okay, so you have only finitely many cases to check. Okay. It is overkill, but it's not really. Okay, good.
Yes, sir.
Okay. It looks funny, but let's. I want you to practice writing things like this. Okay. Okay. Now, the next one. Go back to the. So this one. This one is fine, but refer to this lemma, okay? Rewrite it, but rewrite carefully and then refer to this lemma when needed, okay? Fine, with proof necessary and sufficient. That means so you wanna you find some conditions and you have to verify that when you have those conditions, then you get a probability measure. But then you prove that it is a probability measure, you have to use this lemma. Okay, because the situation boils down to this. Okay. Uh, so this one I show you a solution. This one is fine. So like upgrade the solution for problem 2. Okay. For the problem 3, this is fine. Okay, this is perfect. You have two sets, odds and evens, and yeah, you need to be this, and okay, this is okay. Now, problem 4. go back here. So this part is correct, okay? There's no issues with this. You can write one line saying that to prove the finite heredity, it is enough to verify it for two sets. Okay, that's the thing doing here. Uh, mention that it is enough to verify the finite heredity for two sets. Okay, let's make this problem 30. Okay, now, so this part is, yeah, so this part is correct. And now we have for the part B. What you need, if you start writing things down, you have a, you have a, you will you will run into this proposition. Let A in. Let me not write it here. I'll write it in the so I have the problem 30. Now, when you add uh, when you deal with the countable additivity, so what you'll ended up in end up running into in here is this proposition. Let an k n equals 1 up to, we have a sequence of n and k are both numbers from 1 up to infinity. Okay. Okay. Be positive. Be non-negative. Real numbers. Okay, then this sum n equals 1 up to infinity of this sum k equals 1 up to infinity of a and k is equal to this. Okay. And proposition 2. So the point is, like, if you have whole bunch of positive numbers, you can if you have like you have a double sums like this, then you can switch the double sum. Okay. And then here is the other one. Let an be a sequence non-negative real numbers. Okay. And let phi be a bijection. Okay. Then sum n equals 1 up to infinity, a of phi n is equal to sum n equals 1 up to infinity a. Okay, so the point is like so what this phi does, it is changing the order of the summation. No, not the changing the order, like the, so the when we add here so when you put, let's say, so the phi is a permutation. So phi is so a of phi n is the same sequence a n, but its positions are changed. So but if the numbers are positive real numbers, then this works. Okay. And so corollary to this, let A be a countable set then countable set and A alpha, sorry, and A is just a function from the set A into non-negative numbers, including the plus infinity. Then we can then sum, let's say n in this set capital A, an is well defined. Okay, meaning so let's take you take any function from integers to the set A, then you can any two functions phi and psi, then sum n equals 1 up to infinity a of psi n. This is going to be equal to sum n equals 1 up to infinity a of phi n. So it doesn't matter the order. Okay, and if the set is countable, you can even like not worry about the order of the summations, p bijections. It looks complicated, but this is simply saying that a plus b plus c equals b plus a plus c, something like this is the commutativity. You can, if you have a bunch of finitely many numbers, that we have this, but even for the countable many non-negative numbers, we can have this, and in that that means we don't have to introduce the brackets. So yeah, that means you don't have to even specify order of summation, which element goes first. Okay, so I think these these properties are listed in the appendix of the book. Okay, and typically we go through this in a real analysis course, but I'm not sure if you have done it. Okay, but like when you do this problem, you will run into this. Okay, good. And if you have when you do problem 13, now you try to do it with this in mind, and if you so you write the solution, and then if you use this thing, then go look at the proof. Okay, and then we will go through it again. Okay, now let's go back. Yeah, so problem 6. let's go through problem 6 carefully. So this is the yeah. Okay, so this is the theorem 2.1.1, and thank you for writing the theorem here. So yeah, now in here we are talking about when omega is finite or countable. Okay, the lemma that I had earlier, that was when sigma algebra is finite, not necessarily the omega. Okay, it's countable, is finite or countable non-empty set, and we have a function and it satisfies this here, some omega in capital Omega P of omega equals 1. So for example, when you write this statement here, what I'm using is the corollary. Okay, so you can ask like, so this we have capital Omega, and the capital Omega can be finite. If it is finite, then this sum is finite sum, and we don't have to specify the order of the summation. Order of the, which element we add first. And that corollary tells you that you don't have to, if the omega is, even when the omega is countable, you don't have to specify which element we start adding. Okay? Like writing this is justified by that corollary. So then there is a valid probability triple F is the collection of all the subsets of omega, and for all in F you add the individual elements. Okay, now in the proof, so this one, again, this one is, we have these 4 lines. What you're trying to do, you're trying to verify that power set of omega is a sigma algebra. Okay, and so it is better to write that. It's better to just even mention it. Just say like, first note that capital F is a sigma algebra. You can just write that line and not verify it. But if you verify, you go into verifying, you have to verify all the conditions. You can say like, first note that F equals P of omega is a sigma algebra, since we have this property, we have empty set and omega, both those are in F, and then it's closed under the complements, meaning that if you have element F in the set, F in the sigma algebra, and then its complement is also set, because the complement is again a subset of omega. Now here is this third line is the trouble. Okay, so for sigma algebra you have to work with the countable unions and countable intersections, not just 2 sets. Okay, so you rewrite this thing, and these 4 lines get replaced by showing that P of omega is a sigma algebra. Okay, so now this is the P. So this line is fine, And again, like the reason why we can write things like this is because capital omega is countable or finite. So that means the A has only countable or finitely many uh, elements. So this sum makes sense from the corollary I mentioned. Okay. Okay, so the first property is fine. This line is fine. And okay, so this one is fine. This one is fine. Now we take these guys and this, since AI is a disjoint, omega in here is same as this. Okay, so let me add something to this. So what you're using, it looks like you're using the double sum. And you are. And I think uh, let me write a proposition for this, okay? Let me write this one. Let me write a proposition for this. Let me call it proposition 3. Proposition, we call it 1 delta. So we use the same setup. So the more some n and k in this set, So we have from the proposition 1, we have this, you can exchange the sums, and I'm adding this part here. Because what you're noticing is this n and k, that's also a countable set, where a is equal n cross n. Okay, so the point is you don't have to worry about like in here, it tells you that you don't have to, if you're adding bunch of countable many positive numbers, you don't have to worry about the order. Okay, and this is now this number is itself defined because this set A is countable. It's a countable set, and if this set can be written as a product of two sequences, then we still have this. Okay, and this is the one that you're using in this proof. Go back. So now let's look at this thing very closely. So the first sum here is over it is over a countable set, because the union of AIs that's inside omega, and then omega is countable. Okay, and but you can write this set as a kind of union of I and then elements in AI. So that has the flavor of this double something. Okay, so rewrite it, but refer to these propositions. Okay, and we have problem 7, 8, 9, 10, 11, and let me put that problem 12, and then it's okay, and then problem 20. Okay. Okay, so I have to rewrite this step. Gently. Okay. Yeah, this is something very interesting about me in general. If I were to just teach, I would go fast. But if I know that you're not we don't have the full background, or like, so you're stuck in out there, then I get like very chilled. Okay, good. I go fast, but I don't want to go fast if you're not following. Good. So take some time and then resubmit these things. Okay. Any questions, Ayash?
No, sir.
He's
Okay.
good, right?
Okay. Yeah, it's good.
Yeah, and then we okay. And I'll end the class for today at this point. And again, like it's okay to post this thing and I post it, okay? And I'll stop the recording now and then I can talk with you a little bit more if you have questions.